Hello learners, welcome to today's discussion. Today we are going to look at a topic in Form 4 called electrochemistry. And basically in electrochemistry, this is a topic that deals with how electricity causes chemical reactions and how chemical reactions in turn cause electricity. The question we have reads, use the standard reduction potentials for elements P, Q, R, S, and T given below to answer the questions that follow. The letters do not represent the actual symbols of elements. We have been given the half cells of the elements P, Q, R, S, and T together with their reduction potential values. These values are obtained from the voltmeter when these half cells are connected to the standard reference electrode, which is hydrogen. So the guideline should be, we have those values which are negative, we also have those which are positive. The most negative is the strongest reducing agent, and reducing agents always undergo a process called oxidation, and oxidation takes place at the anode, which is usually placed on the left hand side of the electrochemical cell. Then we have the most positive. The most positive is the strongest oxidizing agent. Oxidizing agents undergo reduction, and reduction usually takes place at the cathode, which is usually placed on the right hand side of the electrochemical cell. Now let us go through these questions together. The first question, which element is likely to be hydrogen? Give a reason. Usually, hydrogen is the one that is used as our reference electrode with an E theta value of 0.00. If you look at the list that we have, you realize the element that has an E theta value of 0 is element R, and therefore that element is likely to be hydrogen. Element R. Reason, we can say its E theta value is 0.0 volts, and as such it is used as a reference electrode. It is used as a reference electrode. We move down. Roman 2, which is the E theta value of the strongest reducing agent? We have already said that the strongest reducing agent is the one that is more negative. We have elements P and Q with negative E theta values, but the highest negative is negative 2.90. Hence, the E theta value of the strongest reducing agent is negative 2.90 volts. Roman 3, Our Form 4 student chose S half cell as the reference half cell. Use the space at the right side of the E theta value in volts to rewrite the E theta values of the above half cells. In this case, the element that is used as our reference half cell is that of R, but the student has chosen to use S. If you look at S, S has an E theta value of positive 0.33, and therefore, for S to be used as our reference electrode, it must have an E theta value of 0 volts. And as such, we take the value of S, that is positive 0.33, we reduce it by the same value of 0.33 for us to take it back to 0 volts. Once we have done that, it means we should also reduce all these other values by 0.33 for them to be referenced to the standard element, which is now S. For T, we take positive 2.86, we reduce it by 0.33, and this one is going to give us positive 2.53 volts. For R, which was initially used as our reference electrode, we take the 0.00, we reduce it by 0.33, and this one is going to be negative 0.33 volts. Next, we go to element Q with negative 2.36. We reduce it by 0.33, and the answer is going to be negative 2.69 volts. And lastly, we take P that has negative 2.90. We reduce it by 0.33 for us to get negative 3.23 volts. These are the E theta values of the following half cells if we decide to use S as our reference half cell. Roman 1 has been done, 2 has been done, 3 has been done. Now we go to Roman 4. We go to Roman 4, which says, in the space provided below, draw a labeled diagram of the electrochemical cell that would be obtained when half cells of element Q and S are combined. In this case, we need to know what elements Q and S are undergoing. If you look at Q, Q has a negative E theta value, suggesting that it is a reducing agent, and reducing agents undergo oxidation. And we have already said that oxidation takes place at the anode, which is placed on the left hand side of the electrochemical cell. We have element S with positive 0.33, suggesting that it's an oxidizing agent. Oxidizing agents undergo reduction, and reduction usually takes place at the cathode, which is usually placed on the right hand side of the electrochemical cell. Because the space is not enough, let us pull it down here. Let us pull this question down here. We do it from here. So what we are going to do, it is to draw the two half cells. These are the containers for the solutions. We have the electrode of this solution. We also have the other electrode in the other solution. But we have said the element that is undergoing oxidation is element Q, and therefore this is the anode, where we have electrode Q, and automatically this becomes electrode S. These are the solutions. The two solutions are usually connected by a salt bridge. Then if this is electrode S, then this should be a solution containing the ions of S. And if this is Q, then the solution should contain the ions of Q. The two electrodes are connected to each other via the voltmeter using the connecting wires, and by so doing you have drawn a cell diagram for the combination of Q and S. The next thing that we are supposed to do, you could be asked to calculate the EMF of the cell formed when Q and S are combined. And assuming you've been told to calculate the electromotive force of this cell, then the EMF is given by the E theta of the substance undergoing reduction. You subtract the E theta of the value undergoing oxidation. And in this case now, the E theta value of the substance undergoing reduction is that of S, which has positive 0.33. Then we minus the E theta value of the substance undergoing oxidation, and in this case we have element Q, which has an E theta value of negative 2.36. And if you add the two, because a negative and a negative becomes a plus, this one is going to give us positive. This one is going to give us positive 2.69 volts. That is if you were asked to calculate the electromotive force of the cell formed when Q and S are combined. Let us look at part B of the question. An iron spoon is placed in an electrochemical cell with gold chloride solution to be gold plated. How long must the spoon be in electrolytic cell if the spoon is to be plated with 0.293 grams of gold and the current of the cell is 1.03 amperes? We've been given the relative atomic mass of gold as 197, and 1 Faraday is equivalent to 96,485 coulombs. One thing that we should know is that gold ions will accept 3 electrons for us to have a deposit of gold, which is now a solid. And we know 1 electron requires 96,485 coulombs of electricity. If now gold requires to gain 3 electrons, 3 electrons are going to be equal to 3 times 96,485, which is going to give us 289,453 coulombs. From there, we know that 289,453 coulombs is the amount of electricity required to deposit 1 mole of gold, and 1 mole of gold is exactly 197 grams. So if 197 grams requires 289, 453. What about 0.293? Because that is the mass we want to deposit. 0.293 will be equal to 0.293 we multiply by 289, 453, everything divided by 197. And if you work out this one, you are going to get 430.5 coulombs. Remember, this is the quantity of electricity that is required to deposit 0.293 grams. And we know to get the quantity of electricity, we usually take the current, we multiply by the time. Remember, we have the value of Q, which is 430.5, and this one must be equal to the current of 1.03. We multiply by the time because we are supposed to calculate how long the spoon must be in the electrolytic cell. For us to get the value of T, we divide by 0. That is 1.03 on both sides, where 1.03 and 1.03 cancels for us to get the value of T, and T is going to be equal to 430.5 divided by 1.03, and this gives us approximately 418 seconds. That is the answer to this particular part of the question. Thank you for watching and welcome to our channel. And in case you haven't subscribed, kindly click the subscribe button. And in case you have questions regarding this particular topic, kindly interact with the channel in the comment section, and we shall be glad to address your concerns accordingly.